Thank you very much, Shita bro, for inviting me. And thanks a lot for joining the post-lunch session. So as Niloy was saying, this is the best time to have a afternoon siesta after that great lunch that we had. But anyway, we are here. And I was listening to the talks being given in the morning session. And then at that moment itself, I felt like my talk is going to be, kind of a reverse gear. So you have to, you go forward and then you take a U-turn. It's like we are kind of in a time machine and trying to go back and look into some of the things that those two speakers have spoken about in the morning session. So we will categorically try to see some of the answers to the questions that they put forward and some of the questions that you had put forward, like what are these parameters, billions, millions, where are they inside these models? What is this learning about that Niloy was pointing out? Then Ravi was pointing about text processing. Okay, so somebody asked from the audience, what is Roberta? Okay, so these are some of the questions that we are going to start off with. And then I'll do two case studies. The first one is kind of something that I work on, but has relations to some of the questions that you had asked in the morning. And the second one is more tied to the bits and scripts idea that this workshop is about. So far we have, I think we have looked into large language models. I mean, people have been talking about large language models in the last two sessions, and we saw some of their abilities. Okay. Now, in the area of natural language processing, which is where this large language models research mostly come from, the holy grail is the following task. Can anyone guess from the students what is this task? Translation. Okay. So, and more appropriately, translation by a machine rather than a human being. And therefore, the name machine translation. And all the large language models that people were talking about are based on a very special category of machine learning models, which are called transformers. Okay. And all the LLMs that the present day LLMs that we see are some variants of these transformers. So how do they look like? So remember Niloy was talking about, so if you recall, at some point, Niloy was referring to words like encoders and decoders, right? Somebody also asked from the audience, what is an encoder? Okay. So basically, say this is the input in some language. Which language is this, by the way? French. Okay. So the encoder kind of takes the input in some language, does some processing on it. Okay. This is the computer part. Okay. Does some processing on it, passes it to a decoder, which kind of decodes it to some destination language, in this case, English. So the idea of encoder-decoder is similar to how you send messages in an encrypted way, right? So you change the message into some form, say, for instance, on telegraph or something like that, or telephones, you change it into some signals, and then at the receiving end, the signal is again changed back to the voice of the person you are listening to. Okay. Now, interesting part of this transformer architecture is that it's not one single encoder. There are multiple such encoders stacked over one another. Okay. Similarly, there are multiple such decoders stacked over one another. Fine. And these encoders speak to these decoders. So this is from where the name transformer comes in. It's as if you see an electric transformer, like sockets after sockets after sockets and things like that. Okay. So there are a bunch of encoders and then there are a bunch of decoders. Okay. So now all this interesting properties of large language models that Niloy and Ravi were showing in the first half comes from this very intriguing property of natural languages or text, for instance, which is called self-attention. So something like this was also talked about in Niloy's lecture. He said self-supervision, remember? Yeah. So it's something very similar. So you have a self-attention. In every encoder, if you blow up, there is a self-attention and there is something after that, another small learning module after that, which is passed on to the next encoder. And it goes up and up into the encoder layers. In the decoder, there is a self-attention, a similar self-attention, an encoder-decoder attention, and a feed-forward. Okay? So this is how the encoder and the decoder looks like if you blow them up slightly. Now, if I remove this encoder-decoder attention block, okay, how do these encoders and decoders differ? I have just removed this. After that, how do they differ? I just remove this. Just cut it off. It will be the encoder. Okay. So the encoder and the decoder, in principle, looks very similar. This gives the LLMs their power. We will see how they exploit this power. Okay. So just with the exception that there is a encoder-decoder additional layer here. So now, so Ravi said that he promised that he would not do any maths. So I cannot promise so far, but I'm just trying to limit myself to vectors and matrices and multiplication between matrices. That's all we are going to see. Okay. And that is all what these LLMs do internally. So basically, each of this word here is thought to have an internal representation. You see these cells here? So computers can process what? Only numbers, zeros and ones finally, okay? So you have to somehow change these guys to numbers. So one way of doing them is to represent them by these cellular blocks. These are called vectors, or a more common name, I'm sure many of you have heard. Many of you have heard. Almost anyone in the audience, huh? That's a more computer science stuff. More like, social stuff these days. Embeddings. Have you heard about the word embeddings? So these are nothing but embeddings. And as you pass it through the different layers of the transformer, the embeddings become richer and richer. That means the vectors become richer and richer in their representation of these individual words. Okay, so now what is this idea of self-attention? Let's look through with this example. Suppose you have a sentence like this, okay? The animal didn't cross the street because it was too tired. You see the problem in this sentence? Any problem while translating? It's already hinted whether this it refers to street or to animal. Okay? So for us, it's very easy to make this connection, make this resolution. But believe me, for computers, this is hellishly difficult. So in order to have a solution to this, a set of people came up with this idea of self-attention. Basically, as if every word is trying to look into all other words in the future. Okay? And this comes from the pre-training data. So this is free data that Niloy was telling. You see, this text is already there. I have just shifted the text as if. Okay? So, what are the words that are attending to the word eat? All the words. Fine. Then to animal. So from animal to, because, so you see, the idea is like this. So the will attend to all the words except probably for the, okay, and so on and so forth. It can also have a separate link from the to the, just attending itself. Fine. So every word is as if attending to every other words. That's where the name self-attention comes in. So I am aware, or I am making myself aware of what are the other words in my dash in the sentence. Niloy hinted upon this word. In my neighborhood. What are the words in my neighborhood? In linguistics, we call this context. Okay, fine. What are the words that are in my context? So I am being very careful about my context. What other words appear in my context? Okay, and by being more careful about this context, can I build a better representation of the original embeddings? I start with some embeddings. Niloy said you could start with random embeddings. You start with random, and then by focusing my attention more and more on my neighborhood, can I make a better representation? That's the idea. Okay, so here comes the bit of maths, only though that too only through pictures. So you have these initial vectors, okay? Fine, these initial vectors or embeddings. From there, we construct 3 different vectors. Q1, K1 and V1. Q1s are called queries. Keys are K1s and V's are values. As if, so think of a search engine. What search engines do you know of? Google. You put a query. Okay. What is Google doing then roughly? Any thoughts? In terms of these keys and values? What does this meta search mean? Similar to our query. Similar to our query, right? So, and the database that it is searching, this set is called the set of, in terms of this particular picture. In the context, again, let's be in the context. In context of this particular picture, this is the set of keys, okay? So you have the query and you have a bunch of keys. You are matching the query with the key, and whatever value matches or whatever key matches best, you return the corresponding value as the top result of the search engine. Everybody with me? Okay, so that's how things happen in search engines also. The same idea is being exploited here. So you have a query. All these now are, so there it was like a real query that you were typing. Here, all this machine is internally doing in terms of vectors or embeddings. And it does so by multiplying them, by multiplying these initial random vectors, what you say, with 3 different matrices. Okay? See, WQ, you multiply X1 into WQ, okay, this vector into this matrix, you get Q1. You multiply X2 into WQ, you get Q2. Similarly, K1, you get X1 into WK, and X2 into WK, you get K1 and K2. Similarly, V1 and V2. So there are some matrices sitting out there. And remember the parameters that Ravi was talking about? Recall that you are telling 7 billion parameters, 15 billion parameters and things like that. So these are nothing but the sizes of these matrices, the dimensions of these matrices. And you start off with kind of a blank slate. Okay? You start off with a blank slate. There is like it could be starting off with random vectors out there, okay, or random values in all the cells. And then you will have to train the model to enrich the entries of these matrices. 7 billion such matrices. So basically, in a nutshell, all the neural network drama that you hear about is nothing but vector matrix multiplications of different forms and learning the contents of this matrix suitably. These are also called the parameter matrices. Right? So now, what we do is you have the x1, the original vector, you have the query, you have the key, and you have the value. First thing that you do is you score the keys with respect to your query. That is what we do in search engines also, right? What do? We get the query, we match it with the set of keys that I have. So that is what I am doing here. I do a scoring. Then after scoring, I do 2 steps of normalization. First normalization is basically dividing by the size of these vectors, okay? So that it does not explode, the values don't become very big. Fine. And then in this step, I make all the values in such a way so that they sum to 1. So this is a probability distribution. So this function actually gives me a probability distribution. And you see that this probability distribution kind of tells you like where is the self-attention going most. Okay. So you multiply these probability values with the value vector now. And can you tell me why this is hazy and this is more dark? This is dark, this is hazy. So this is 0.88 into the value and this is 0.12 into the value, right? So this one becomes more pronounced. Fine. And why does this one becomes more pronounced? We are doing it for this word, mind you. So you read it as a linguist, you read it like this. Thinking is putting its highest attention on itself. That's why thinking's value for thinking is maximum. Okay? Thinking's value for machine is this much, and so on and so forth. Basically, in the zeroth context, or it's as if like you can think yourself as your zeroth neighbor, right? So in the zeroth context, it is giving the highest value and the value decays after that. Finally, you get a sum of...
Yes, sir, I did not get that point of thinking giving itself the highest self-attention.
Yeah, so that is what is happening. You see, if you have the... So you want to train your model in this way. Okay, you want to learn your vectors so that... So your self-attention actually drives that thinking. Self means what? I'm giving most attention to myself. So therefore, thinking should be... The value corresponding to thinking should be the largest as compared to all other values when you are considering the first position in the sentence.
Then why only specifically thinking? It could be machines also, right?
No. See, it's self-attention. Thinking is self. Okay? I am giving most attention to myself in the first sense, in the first stage. Okay? And then it will iterate and change over time. That's why we have so many layers of encoders. So that thinking can also, give some attention to other members in its neighborhood. Okay? And in this way, you then finally sum and get the final vectors. Okay? So this is again showing the calculation in terms of matrices. You have the inputs. Okay? You multiply them with the 3 matrices. These are the parameters that you need to learn. And then from there, you get the Q, K, and V matrices. Okay? These are the combination of the individual Qs, Ks, and Vs. Okay? And then finally you get a output. So the output is obtained by doing the softmax of the product, normalized by root decay, and then multiply by the value. Okay? This comes as the final vector. So this is the output of the first layer. Now this goes into the second layer, and the same thing happens. So you remember there were 6 layers of encoders, right? So, and you keep on doing this, but then there is one issue here that if you start with one single guess of these matrices, WQ, WK, and WV, you might be getting a bit biased. So it is better that I start with multiple such initializations of matrices. Okay. So how about having one set W0 QKV, another set W1 QKV, and so on and so forth. So we can have many such heads. Typically we have 8 such heads. That's why it is called multi-head self-attention. Initially it was self-attention, now it becomes multi-head self-attention. Okay. So multiple heads, every head is having its own individual matrices. So you think how many parameters? 7 billion matrix size each, and then you have 8 such 7 billion matrices. And all this you have to train together. Huh? It's just empirical. Now you get the 8 output vectors, you concatenate them and make one single vector out of them. Okay, and this is more or less the whole thing shown in a nutshell. The whole picture that I discussed so far is shown in a nutshell. Okay, so now if you look at the same picture as earlier, you will see that after like many iterations of the model, you will see the coloring of the edges and the different words has become like this. Any clues? What this shows? What this self-attention has done to these links?
Based on that score and the probability distribution that we covered.
Same as the score and the probability distributions, but iterated many times. Huh? It's tired. No? So look at the colors. Look at the color coding. And look at this word it. And what is it getting connected to most? See, animal is one word which is attending to it. Okay? And street is another word. There are some other words after it also which are attending to it, but street is another word. In this spectrum, you see, this is the only one which is green in color. Okay? Street is another word which is attending to it. Why there are 2 color schemes? For the word it, what are the different types of contexts it has? 2 types of contexts. What are they? Huh? Not only that. Look at the word it, okay, in the middle of the sentence. Left and right. So you have a left context and a right context. You have left people living on your left and people living on your right. Right? So one is showing the left context and the other is showing the right context. Okay.
If you have more than 2 contexts.
Usually for a single word, you don't have more than 2 contexts. That happens when you have images. When you have pixeled images, you have 8 contexts. You can have even more. For sentences, it's like very easy. You have only 2 contexts, left and right. Okay, so now so there is some more that needs to be done with the initial processing of the embeddings. So basically, what happens is that when you are doing this encoding of the words, so this sentential form is lost. Why do I say so? What is there in this? What is so intriguing about this sentence structure? Can I write the it in the beginning of that sentence? The order of the words are very important. In some languages, they are much more important, like English, whereas in some other languages, they are less important. So this is the word order structure. So there is as if a temporal ordering in the way the words are spoken. Okay? You cannot say, I rice it. It has to be I eat rice. Syntactically, the other one is wrong. Okay? So there is a temporal ordering in which you can utter your words. So you have to impose this ordering. This ordering is not implicit in this model. So for that, in addition to these initial vectors and whatever we did, we also add a positional information. Okay, this is called positional encoding. So with the initial vectors, we add the positional encoding, and then after the positional encoding are put in, we pass it through the self-attention. And then we pass it through a feed forward and forward it to the next steps. Okay. So, and the other side is the decoder. Decoder is very similar to the encoder except that one single layer. Which layer? The encoder-decoder attention, the cross attention. Okay. That has to be modeled separately in the decoder. Otherwise, the encoder and decoder are just symmetric to one another. Okay. So what you do for the encoder-decoder self-attention, you just change the query and the key values. Here, the query comes from the again, this is a search engine problem. Query comes as if from the encoder. Where is the search taking place? In the decoder. You search the corresponding key, the closest key in the decoder, and you return the decoder's value. That way your translation automatically takes place. As if you are searching in French, your keys are all in English, somehow you do some transformation and you compare it with the English and then return the answer in English. So this is how it's mapped to a query key value setting. That is what is being done in the encoder-decoder layer. Okay, the additional thing. And then we pass it through, and as Niloy was saying, that for each of these words that we output, there is a probability associated. The word with the highest probability in your vocabulary is output at the beginning, and so on and so forth. Now, see, there is an intriguing thing. So suppose I don't have the encoder at all. I don't have the encoder at all. Can I still train just the decoder? No encoder is there. No query is coming from the encoder. Any thoughts? See, as I say, they are very similar in structure. So that idea you have to leverage here. How can I just forget the encoder? Say I'm not doing the translation problem, some other problem. Say sentence completion. Now can you think? I start some words and then I want the machine to complete it. See, what is the decoder in practice doing? It is first giving the output I, then giving am. The moment it is giving output I, can I bring it to the input of the decoder again? The output is as if fed back to the input of the decoder. And in this way, a chain reaction takes place. This is the generative part. That is why we are all the time talking about Gen AI. This is the generation that is taking place. Okay. So you take the input or the output coming from the decoder and pass it as the input and try to predict the next word. So you kind of do not have the decoder at all. Okay. Sorry, the encoder at all. So now, so this is more or less a basic non-mathematical primer to transformers. I mean, almost non-mathematical primer to transformers. Now, depending on your choices of whether you are using only the encoder, or you are using both encoder and decoder, or you are using only the decoder, different types of large language models are available. So, the encoder-only transformers are the types that you were asking about. BERT, Robert, these are encoder-only. They don't have the decoder part. They have only the encoder part. So, the encoder part will give what at the end? At the end, it will give you. Will it give you a translation? A complete translation? You have only the encoder. Just this. What does this give as the output? A vector of numbers, which is uninterpretable by us. Okay, only machines interpret. That's why the name encoder. Give some text, it gives you a vector of numbers. And BERT-like models do this. Then there are these T5 models, which are having both the encoder as well as decoder. And then there is this place where OpenAI is doing all its business, okay, and many other companies, Google, etc. Okay, these are the decoder-only models. You have only the decoder, no encoder here. These are GPT series models. What is the full form of GPT? Generative Pre-trained Transformers. This is what we have learned so far, transformers. The basic principle of working of the transformers is like this. Fine. Okay. So now, as I said, we will go into a case study, but Shita bro, is it the best time to take a short break and then go? Okay, so I'm not sure if I would be able to do 2 case studies. But let's see if they have any questions first. No questions? Yeah.
So just the way we could use a decoder for performing both the tasks for encoder as well by providing the output of what the decoder gives as an input to it again. Can we do the same thing for encoder?
So encoder gives you a vector.
Yes.
After that, you can play with that vector. It's a representation at the end of the day. Then you can pass it to a standard machine learning model to do anything. Like as Niloy was telling, sentiment classification or something. Some arbitrary work. Okay. This encoder part is doing all the pre-training business. Then you can give it to some XYZ to do, which it can do. Okay, let's do it in this way. So if you have any further questions, we can take it now. Yes?
So do the AI engineers play around with the decoder to tweak their algorithms and stuff?
They tweak with everything. They tweak starting from the data, from the pre-training data, they tweak with everything. They tweak with encoders, they tweak with decoders, they tweak with both the encoder, decoder, they tweak with self-attention, cross-attention, everything. Okay? Every other part in this whole architecture is a variable.
So the matrices which you showed, the W matrices, the size of those depend on the query as well as the key.
So yeah, these are all predefined. So basically, see, if you have, say,
how can we calculate the parameters?
No, so the parameters are determined by the matrix size.
Yeah.
The vectors are determined by the kind of input or the length of the input or the number of tokens that it has to handle. Say, for instance, I guess GPT-4 allows 4096 tokens, which is around 5000 or 4100 tokens, right? So, like, depending on that, see, if you try to shrink the query to just 4 size vectors, it will not work. You have to think about a good dimension. So, typically people work with 512 or 1024 kind of vector dimensions. So, that is kind of the vector, okay? Now, when you are doing multiplication, you need to have the dimensionality match, right?
Yes.
There you expand, okay? So, there you kind of expand the original input vector into a larger vector and then you multiply and then again you squeeze.
Okay, so I was trying to understand in terms of the slide you showed.
Yeah.
So there was this key.
This is the part.
Now the previous, the one which had all the 3 things. Initial ones, I think.
This one, right?
Yeah, then you had this one. So here, for example, this X, this queries, keys, etc. These are the vectors shown, and then these are the W matrices.
Yes.
These like this is just arbitrarily shown like this.
Yeah, it is arbitrarily showed here. This is a hypothetical example.
Yeah.
But then ultimately what you do, See, what I have cunningly skipped here is this part. But this part is also very important. This is called layer normalization. In the layer normalization, you actually try to balance these sizes so that they have the parity with the matrices when you multiply them.
Yes.
Okay. Okay. Any other questions? Otherwise, we will take off with the next part. Okay. So, let's take away with the next part of the case studies. So, I'll try to quickly go through both the case studies. Let's see how quickly we can do it. So, one is because it's a very important societal problem as far as my perception, and the other is like something tied to the workshop's spirit. So, if you recall, in the morning lectures, Ravi was talking about this LLMs generating toxicity. So, and as I said, that these LLMs could be used for not only doing text generation, right? They are now used for every other task in machine learning that you can think of, starting from sentiment classification and things like that. Okay. So, this is one case study that we did. So, I guess everybody has a notion of what is hate speech. So, this is like the entire online world is inflicted by different forms of hate speech, which could be like sometimes translating itself to real violences. Okay, some examples are cited, and also there are effects that are purely psychological. Fine. So these problems have kind of become the order of the day, and therefore all these big platforms, starting from Meta, Google, okay, especially the social media platforms X, they have started using large language models to moderate hate speech, okay, to filter. So as if the hate speech is first, the moment it is posted, it is passed through this kind of an LLM, and the LLM says, yes, it is hate, you bar it. LLM says, no, it's not hate, you allow it. Okay. Now the question is, how good are these LLMs in doing this task? That was the precise question that we asked. So, in order to do this, this is what I just now explained. So, basically, when you have to ask the LLMs, you have to ask in terms of pieces of text which are called prompts. You prompt, so many of you have used ChatGPT, right? So, you give a prompt and the LLM gives you some output. Okay. So, you prompt the LLMs and then you expect some answer from the LLMs. Okay. So, we try to see whether if we prompt the LLM with the task of identifying whether a piece of text is hateful or not, what is it doing? Okay. So, for that, this was a work which we published last year. So, and we said that we will use the LLMs as is. We will not train them. People have started saying that they have they have become omnipotent. So they can be used for any task, so to say. So therefore, we thought that why don't we take these LLMs and see if they are really so. So what we did was we gave some prompts and we had some hate speech datasets that we already collected earlier. Okay, some by our own efforts and some from other groups. And then we passed it to the LLM and asked the LLM this simple question: do you think that this piece of text that I am giving you, is it hateful or not hateful? And then we looked into the cases where the LLMs misclassified, went wrong. And we tried to see what are these cases where the LLMs went wrong, so that we could give a suggestion as to what are the vulnerabilities of these models. Okay, so we took three data sets. One is called the implicit hate. Okay, so hatefulness could be both implicit as well as explicit, right? Sometimes it's very explicit, there are vulgar words. Sometimes it is very implicit. Like the sentence, 6 million was not enough. Anyone guesses whether this is a hate speech or not? This piece of text, say you tweet, 6 million was not enough. it's hate speech. There is no context. Even no context is required. It's hate speech. So this is talking about the 6 million people who were kind of slaughtered during the Holocaust. So if you say 6 million was not enough and give it to some like XYZ sentiment analyzer, it will say that this sentence has neutral sentiment. It will not be able to detect the subjectivity of the task. Okay. So we ask that how powerful these LLMs are. So there are many such implicit texts which could be highly hateful. Okay. So and then we had one dataset that was released by us, and then the third one that was released by some of our collaborators working in some other group. And in all of this, the good part was that the annotators did not only mark whether the sentence is hateful or not, or the text is hateful or not, but also marked the position as to which corresponds to the helpfulness. So basically the annotator said that this is the part of the text which I feel makes this whole text hateful. Okay. So this is also called the rationale. Okay. The rationale of calling something hateful or calling something something. Okay. This is the linguistic rationale of calling something something. So basically these green boxes, highlights that you see here are the explanations or the rationales that the annotators are giving us. So now we asked the LLMs questions in different ways. So you can vary your prompts. You are sitting as an adversary here. So this is like an adversarial setup. You are sitting as an adversary here, and you can vary your prompts and ask the LLM different questions regarding the same target answer you require, whether it's hateful or not. Okay, but you can ask the question in different ways. You are free. So we asked it in different ways, like we gave vanilla questions. We gave the definition of what is hateful to the LLM. This is additionally fed. Although LLMs should know, because of the big data set that they're pre-trained on, LLMs should know what the definition of hate speech is, but still we gave them. Then we asked the LLM, okay, you are telling this is hateful. Can you explain why this is hateful? Why do you think this is hateful? Sometimes we gave the explanation that you saw in the last slide. Since we had those, the rationales, we gave the rationale also. We say this is the input, this is the rationale. Now tell me whether this is hateful or not. So this is what is explanation at input. The other one is you give only the text and ask the LLM, tell me whether it is hateful or not, and also explain your answer. So that's explanation as output. And then you also sometimes can ask, can you tell me whether this or to which community is this hate speech targeting? So for instance, 6 million was not enough. Which community is it? The Jewish community. Okay. So can the LLM figure out which community this text or this post is targeting? That's the question that we ask. Sometimes we give that as input and then ask, can you now tell me whether it's hateful or not? And sometimes we ask the LLM, give me the output. So we do all these play arounds. And then each of these have their own labels. So for instance, hate explain has normal, offensive, and hate speech as the different categories. Implicit hate has explicit hate, implicit hate or not hate. Toxic to spam has 2 categories, toxic or non-toxic. These are the posts, different types of posts that you find in these data sets. And now we have a bunch of prompts, and we ask the LLMs that given this post and given this question, can you give me the label, whether it's hateful or not hateful? And then we compare it with the ground truth. That is what we have got from the annotated data annotated by humans. So we did it for different types of prompts. For paucity of time, I'm not going into all of this. And then we also mix like definition with explanation, then target with definition and things like that. And then these are some of the large language models that we have tested our experiments, that we have tested for our experiments. The GPT 3.5, Text Da Vinci, which is just a precursor of GPT 3.5, and then Flan T5. So this is the T5 family, which has both encoder and decoder. And these two both are GPT-based models. It only has the decoder. And then we study the performance through different metrics. I'm not going into the details. But then what we are seeing is the detection accuracy of all these models, okay. So think of this is the performance. 1 is the best, 0 is the worst. Okay. And this is for the hate explained data, the first data set. What do you think? Is this performance acceptable? The best model is giving you somewhere slightly larger than 60%. Should this be used by companies? And that for the combination, you have a definition and the target also given as input. You give that 6 million was not enough, comma GUs, this is the entire input. Now you ask whether it's hateful or not. So you're already giving the target as the clue, plus the post and the prompt. Okay. And also the definition of what is hate speech and what is not. Even then, the performance is stuck at 60. So 61% is a good performance value. When 100% is the requirement. So typically, machine learning models these days, like what is the performance that you can think of? Do you have any idea? I mean, when is it becoming acceptable? Say at the industry level. Typically. Or let's rephrase the question. What will be the number you will be happy with? Suppose Meta is wanting to deploy this or X is wanting to deploy this. Closer to 1, nothing less than 80%, right? Nothing less than 80%. But you see, we are stuck at, so all these are very large models with like 7 billion, so such large matrices. But still, with this, so what is the difference between sentiment classification and this problem? So in sentiment classification, you go to so you use these LLMs, you can reach 90% plus accuracy, but here it's stuck at 60%. What is the difference from a vanilla sentiment classification problem? Why is this problem so intriguing? It's also a simple classification. What is hateful, what is not. In fact, probably it's easier. Sentiment might be positive, negative, or neutral. The training set was, but we have not even seen the result. I mean, the output texts. So it's difficult to comment from the performance whether it's biased or not. It's low, but it could be the performance could be low on all targets. Yes. So in sentiment analysis also the test set is human annotated. The models are also only pre-trained. They are not trained on sentiment analysis data. Yes, that's true for sentiment analysis as well as for hate speech. It's the same pre-trained data that are being used. That's one point. Things are evolving, language is changing, and that change gets reflected much faster in this kind of post compared to sentiments, which are more laden or latent concepts. The other thing is that these are far more subjective tasks compared to sentiment analysis. So, yeah, we went on doing for the other data sets also, but the results are pretty much stuck to 60-65%. The only place where we do a little bit better is the toxic span data. Any guesses why? Very good. So this had, if you remember, only 2 levels, toxic and non-toxic, where the others had 3 levels. If I go back, the other 2 data sets had, so do you think it's very easy to differentiate between implicit and explicit hate? Is it so easy? So these are 2 different levels. Similarly, offensive, what is offensive and what is hate speech? It's even difficult for humans to understand it. Leave alone machines. Yeah. So then what we did was we tried to see what are these misclassified cases. Okay, can we make sense out of these misclassified cases? That was the question that we... So the 40% cases that you saw, which were all misclassified, we took them. We also saw where the machine is miserably badly explaining its output. So we had our explanations in the dataset in the form of rationales. We compared those explanations with the explanation that machine gave. And we saw where this similarity is very poor between the explanations generated by the machine and the explanation given by the annotators. We saw these two things together, the misclassified data and on top of it, whether it is badly explained. We took these two things and we took all such data points and clustered them using some standard topical clustering. And these are some of the... So this is kind of like some of the most interesting observations that I feel came out of this study. So if you look at the implicit hate data set, these are some of the misclassified posts. Okay? So the ground truth was not hate. The prediction was implicit hate. The ground truth was not hate. The prediction was implicit hate. Again, same thing here. Again, same thing here. So what do you see is happening? Why so many errors in the model? So the errors could be attributed to... So we say it's not better than 60%. What are the most of the errors coming from? At least in this data set. See, not hate, implicit hate, not hate, implicit hate, not hate, implicit hate. Does this not trigger something? All the not hates are being categorized as implicit hate. So the model is over apprehensive. जो भी आएगा hateful बोल दूंगा. Whatever comes to me, I'll tell hateful. Then my job is done. Don't know, don't care how well it is done or not. So now you post anything related to racism which has nothing to do, nothing hateful in it. Okay, some simple vanilla newspaper text or something which is pro-white, as like if I recall, Ravi was also showing like all the images that you ask for generation, even the Nazi soldiers, they would like generate a black woman. Same thing here. You see, like you are speaking about white, nothing. There is no discriminatory statement or nothing hateful in those statements. Okay, but still, it is categorized as hateful. So the model is over-triggering or it's over-apprehensive. For the hate explained data set, it's again, see, offensive. So this is a very interesting case. One of you, I think, pointed out to Niloy about this not situation. So anything that is not should have a positive sentiment. That's not always true. And this is the example for that. See, it's telling nor and neither. The moment it is telling these two, the model starts feeling that this has nothing to do with hatefulness. So it's a negation of hatefulness. And the moment it does this negation, it applies its own negation intelligence, it marks it as non-hateful. Okay, it should have been offensive, but it marks it as non-hateful because of the sheer presence of this one also, no nigger. So the N word is there and it's definitely hateful, but since there is this no here, it has called it not hateful. Okay. So you see the errors that it makes, as Ravi was telling, how confidently it makes its errors. So the same thing for the third one also, third data set also. Yeah, I'll skip over this one. Yeah, then coming to the last case study, which is kind of probably related to bits and scripts to some extent. So this is not by us, but this is by some other group, which were like trying to identify native languages and exploit the power of large language models in identifying native languages. Now how? By looking at how these native language speakers write English. So they write a foreign language, and these foreign language scripts are given to you, okay? And you have to tell me what is the native language of the speaker who has written this English, okay? That's the question you are posing. Now we are asking, like, can LLMs do something in this kind of a task? Can LLMs tell us with some confidence what is the native language of the writer, okay? Yeah, so this is the task in a nutshell. This is also called the NLI task, native language identification. So you have English text fed in to the learning model, and it will tell with some accuracy which text is written by which of these authors. And L1 here refers to, L1 is linguists, this group, the native language. L2 is the second language. Okay. So the data set that these authors took is from TOEFL 11. So this has 1100 English essays that were like written by people or language communities from 11 diverse languages, okay, starting from Arabic to Chinese, French, German, etc. Okay, and 100 essays were collected from each of these 11 language communities. Okay, and the writers had different English proficiency. Some of them had low proficiency, some of them had medium, some of them had high. Okay, roughly 348 words, and the authors tested two models. Okay, GPT 3.5 and GPT 4. So what did they ask? They again cooked some prompts. So the first prompt is, it is telling that you are a forensic linguistics expert that reads English texts written by non-native authors in order to classify the native language of the author. And then you give the choice of all the languages. Okay. You also tell that you should identify the native language from the patterns of word choice, syntactic patterns and errors, grammatical errors, spelling errors, and things like that. So some language community makes certain types of linguistic errors while writing the L2 language. Okay, this is what the model is asked to pick up from. Okay. And then they are also telling that do not use any other class. So with this prompt, this was their success. It's a good success. So while hate was more hazy, there was less promise there. Seems like there is more promise here. So GPT-4 is able to identify the native language with 91.7% accuracy, which I would say is pretty decent. Now, where does it go wrong? Okay, so if you take the confusion matrix of which language is confused with which other language, what you see is Hindi and Telugu are most confused. Any linguist in this audience? I also really don't know. I mean, this is not my work, but this needs investigation. Why this Telugu was confused by Hindi? You see, 35 cases. Out of 200 essays, 100 from Hindi and 100 from Telugu. Yeah, these are related languages. That's true. Could be. Yeah. So, but this is a place where investigation could be done. Okay, interesting investigation could be done. There is also that's actually that is what we'll come to in the next set of experiments that the authors did. And the second one is more understandable. It's the Sino-Tibetan group that is being confused with one another. Okay. So now, if you recall the previous prompt, they made it clear to the model that you can predict only from this set of languages. Now, if I remove this bar, okay, and I tell you predict anything you like, I'm giving you this text, and you predict any language. Okay, this is important when you are trying to discover something new. What is the power of these models in discovering something new that is not there latent in the data? This is probably where it connects better with the bits and scripts theme. Okay, so now in this case, if you do that, if you give it free lunch, you can identify some language and tell me. Might not be from that set of 11 languages. So what do you see? So this is what we call the open set. It's an open set of languages. The performance has dropped, but not so drastically. It's still usable. The source are those 11 languages. But now the target could be anything on the earth. Any of the 6,000 languages. And here you start seeing some very interesting trends and some important advancements. You start looking at some interpretable important advancements from GPT 3.5 to GPT 4. So in GPT 3.5, the authors found that in a large number of essays, the model is predicting that the first language of the author is English. From the English essays, it is predicting that the first language is English. So English is the highest misclassified destination. Fine? That is kind of seems like natural because these are all English texts and they are asked to find out the native language, and the easiest way to probably, the most obvious prediction would be English, right? That is what it is doing in GPT 3.5. But you see in GPT 4, there is not a single case out of these 1100 essays which was classified as written by an English native speaker. So you see, definitely there is an improvement in the model architecture. Otherwise, this could not have happened. So this is an interpretable result which tells you that there is some improvement in the model that has taken place. And some other observations like Tamil is misclassified with Telugu. So Telugu is misclassified as Tamil. Okay, so these are the open set languages. These were our closed set of 11 languages. These are the open sets. So you see Telugu is kind of misclassified with Tamil. Then some of Spanish is misclassified with Portuguese. Like geographically and linguistically close languages are kind of misclassified. Fine? And of course, like you see much less misclassifications in GPT-4. The misclassifications has reduced to a large extent, especially with English as well as with other languages. There are still some 1 or 2 cases, but it's far better than GPT 3.5. Okay, I think I am more or less on time, and I would like to thank my students, Synergy, and the team Hate Alert, which was responsible for the second part of the work that we did. And thanks to all of you for sitting down here for like more than 1.5 hours after the lunch and listening to me. Thank you very much.
Thanks, Animesh. Wonderful talk. We have time for 1 or 2 quick questions before Animesh has to fly to the airport.
Yes.
I think these 2 questions.
Sir, with connection to how LLMs are being used to identify hate speech, LLMs themselves are being attacked using these prompt injection attacks.
Yeah, very good point. Yes.
So can LLMs themselves learn how these prompt injection attacks are used and use them as going back to the decoder and learning from how to prevent that?
Excellent question. So I think one of you asked in the beginning of the session also to Ravindran the same question. So this is called machine unlearning. Okay, and this field is growing up is coming up in a very big way. So where you try to basically unlearn some of the things that you have learned, which probably makes you stereotypical. Okay, and you want to go away or drive yourself far away from the stereotypical behavior. So, and there comes this whole theory of machine learning. If you are interested, you can go back and look into this, where people are using these machine learning theories to reinforce the LLMs to divert from the stereotypical behavior and have this additional knowledge, okay, so that it does not land up into. So this is also called prompt injection is a less fancy term. The more fancy term is red teaming. Okay. So you red team these language models and try to teach the language model from the outcomes of this red teaming.
You mentioned one of the data sources that you used for training the
Testing.
When you were training for hate speech detection, basically, you said
Not
that
trained. We were using zero shot. So the models are used in their base form. We were just asking them, giving the data, test instances, and asking them whether this is hateful or not.
at some point you mentioned that you guys collected data yourself and
Yes,
curated some.
different work. So we used that data set.
Oh, I see. Do you also see the opposite case, by overmarking something as hateful speech, even though it isn't, that can be used to, sort of strategically censor some things?
Very good point. So this is where this brings to the ideas that Niloy was pointing out in the form of contrastive learning. So you could have hard contrasts, you could have soft contrasts. If you have soft contrasts, then the model do not learn the separation very well. Okay, but if you have hard contrasts, say one which is very close to offensive, already at the line, and the other one which is offensive, it's much more hard to detect a difference between these two than something which is blatantly offensive and something which is neutral. Okay, so if you train your models with this, so there are these layers of contrastive learning, and if you train your models with this increasingly higher hard contrasts, probably some of the questions that you are asking will be answered.
I don't know if I missed this, but did you at any point mention bias in the data that could come? Because this seems like a topic where the bias in the data set is
Yes.
good.
So all the data sets that you see here, they are published data sets. People are working on this for long, but bias is something that cannot be completely ignored. For instance, the annotators. Okay, so you can, for hate speech, you can broadly classify the annotators into two meta sets. One set is people who have themselves faced hate speech and people who have never faced hate speech. Okay, so their annotations probably are going to vary a bit. So some of them will find something hateful, especially the ones that are who have faced hate speech or have been victims of hate speech.
You're sort of expecting that.
Yeah, so they will probably be more strict in doing the labelings compared to those who have not. Okay, this is one meta level. Then there are other meta levels, say if the annotator is from the West compared to if the annotator is from the East, there will be differences. Okay, if the annotator is a female compared to male, so there will be some differences. We tried to balance out all these things while doing this annotation task. So we have, in our work, we had 250 plus annotators across the world doing this and from a varied background. So we can expect most of the things so that's why this data set, Hate Explain, is a very highly cited data set because it kind of tries to maintain this balance.
Thanks.
But of course, biases are there still. I don't ignore them.
Sorry.
Sorry of research.
I need to probably cut this off. You can probably ask him while outside because he also needs to get on the taxi to go to the airport. So let's thank the speakers once more.